T-minus 15 seconds and the sound suppression water system has been activated.
Okay.
We have a go from engine start. 3 engines up and ready. 3, 2, 1, 0. Booster ignition and liftoff of Discovery, blazing a trail to scientific discoveries aboard space station.
Houston, Discovery, roll program.
Roger, roll, Discovery.
This is Mission Control, Houston. Space Shuttle Discovery is rolling into a heads-down position, putting it on course for 51.6 degree, 136 by 36 statute line orbit, and eventually the International Space Station. Discovery's 3 liquid-fueled main engines are now throttling down to reduce stress on the shuttle as it travels through the area of maximum dynamic pressure. Discovery is already...
Chapter 19, Thermodynamics. What we're going to study in this chapter is energy as it relates to the spontaneity of processes. They could be physical processes, they can be chemical processes, chemical reactions, and we'll focus on entropy, this strange word that you've no doubt heard before, and we're going to learn something about what entropy is, what the role of entropy is in the spontaneity of different processes. First of all, let's just make a quick run through of the difference between the study of kinetics, which we did in chapter 14, that's rates of reactions, and thermodynamics. So if I were to look at a reaction coordinate, a reaction progress diagram, thermodynamics deals with the directionality of a reaction. Will it occur? Won't it occur? Whereas kinetics in the center here is totally focused on the rates of reaction. So we're just concerned with, will the reaction or will the process occur without outside intervention? Is it spontaneous? And is it spontaneous in the forward direction or the reverse direction? Spontaneous reactions. A process is said to be spontaneous if it occurs without outside intervention. That is, if you establish a given set of conditions, will a process, either physical or chemical, occur? The reaction could be fast, it could be slow. You have plenty of slow reactions that are nevertheless spontaneous. Most spontaneous reactions, but not all, are exothermic, and we're going to look at different reactions. Some are endothermic and spontaneous, some are exothermic and spontaneous. Most spontaneous reactions, but not all, go from higher levels of energy down to lower levels of energy, and in that process they release energy, generally in the form of heat. What other factors are important? Well, entropy is the principal factor that we're going to be looking at in this section. Examples of spontaneity. A ball rolls down a hill. Now, that's definitely a ball going from a higher potential energy to a lower potential energy. So in terms of a chemical reaction, we would call that an exothermic reaction. A gas will spontaneously fill a container uniformly. That is, gases spread out to occupy whatever container, whatever volume of space they're allowed to occupy, and they do so uniformly, where the concentration of the gas is uniform throughout the distribution. Heat flow always occurs from a hot object to a cooler one. It never goes in the opposite direction. Heat always goes from a high concentration of heat, that is high temperature, to a lower concentration of heat, a lower temperature. So if I open my front door on a cold winter's day where it's 20 degrees outside, this is Texas, so 20 degrees is cold, and it's nice toasty 70 degrees in my house, the cold does not rush in through the door. The heat flows out through the door. It goes from high concentration to low concentration. So when your mother said, close the door, don't let the cold in, what she really meant is don't let the heat out. So here's a spontaneous reaction. At a temperature below 0 degrees, water will freeze, and at a temperature above 0 degrees, ice will melt. That is an endothermic process. Heat actually has to flow into the ice to melt it. On the other hand, when water freezes, it goes from a liquid where the molecules of the water are moving at a higher velocity, they have more kinetic energy, they have to slow down, so they have to give up heat. They sit there in place in that crystal vibrating. That is an exothermic process that's spontaneous. So the driving force for a spontaneous process is an increase in the entropy of the universe. This always occurs. That is, if something occurs spontaneously, the entropy of the universe increases. Entropy is abbreviated as a capital S. Entropy can be viewed as a measure of the randomness, disorder, the degree to which matter or energy spreads out, and it all depends on whether that's occurring at high temperature. In that case, matter tends to spread out. If it's happening at low temperature, heat is typically released, and the heat energy, the thermal energy, spreads out, as in exothermic processes. Things just naturally progress from order to disorder. So a concentrated solution will dilute or spread out. If I take a solute, if I take a sugar cube and I put it into water, that sugar cube will naturally dissolve, and gradually the sugar molecules are going to separate, and they will evenly be distributed in that solution. They do it naturally. And when they're all spread out, they have more disorder, more possible arrangements as a dilute solution than the sugar had as a crystal cube up here. This is a very low state of disorder. This is a higher state of disorder. And it always occurs when you dilute a solution or you make a solution. It's just more improbable for everything to stay concentrated and highly ordered. So what we can say, if it's more improbable for everything to be concentrated or highly ordered, that it's just a matter of a statistical probability that things will spread out and be more disordered. Spontaneous reactions under a given set of conditions, a reaction will naturally proceed either in the forward direction from reactants to products, or the reverse direction from products to reactants until the system achieves equilibrium. Thermodynamics is the study of energy changes. Energy drives all reactions. Using thermodynamics, it's possible to predict which reactions will occur spontaneously. Remember, we're not talking about the rate of the reaction. The reaction could be spontaneous and slow, or spontaneous and fast. So let's take a look at the spontaneity of reactions with respect to water changing phases. So water undergoes this spontaneous phase change dependent on the temperature of the water. So at temperatures higher than 0 degrees, water goes from ice, we call that a solid, it's ice, and that's a very orderly system, the ice. So you can see that all the water molecules are lined up like soldiers in formation. This is a highly ordered system. So this is highly ordered. And when it's in a situation where the temperature is higher than 0 degrees, if that's the given set of conditions, water will melt and it will become a liquid. And as a liquid, it will be a more disordered system. So what does it mean to be disordered? It just means that there are more possible arrangements for the particles of water. They could be here, they could be here. They're moving faster. So they're moving faster. They have more kinetic energy. It's a more disordered system. And so in this way, at the higher temperature, the matter is becoming more disordered. At temperatures lower than 0 degrees, we take liquid water and it freezes. Now, in order for the liquid water to freeze, it organizes into a much more orderly system. So this starts out at a higher level of entropy. So this is higher disorder or higher entropy. higher disorder, and it goes to a system of lower disorder or lower entropy. And you can take a look at that, and you can see that all these crystals have lined up. There are fewer possible arrangements. A water molecule will simply sit in one location and it vibrates. It never stops moving. It always has residual kinetic energy unless you bring it down to 0 Kelvin, but it'll have a lower entropy as ice than it does as water. And this set of conditions was simply a temperature lower than 0 degrees. At temperatures higher than 100 degrees Celsius, liquid water will vaporize. So this is a vaporization. In this particular case, the liquid water is in a lower state of disorder or a lower entropy. You can sort of use those words interchangeably. It works. And then changes into a gas at temperatures higher than 100 degrees Celsius, and now you have much more disorder and higher entropy. What is the advantage of a liquid and a gas phase at higher temperatures? Greater disorder, greater entropy. What is the advantage of the liquid and the gas phases at higher temperatures? Higher entropy. They are in a more disordered state. Spontaneous spread of energy. The second law of thermodynamics, that is the big kahuna of the entropy laws, the second law of thermodynamics. And we've mentioned it before, but not by name. Here's the deal. The entropy, and you can think of this as randomness, disorder, more possible arrangements, the entropy of the universe. This is a big deal. The whole universe increases for any spontaneous process. Now, a system, a separate system, may actually acquire order. You are a very ordered system. So a system can acquire order. However, if the system spontaneously becomes more ordered, then the entropy of the universe has to increase in that process. Generally speaking, if a system is becoming more ordered, it releases heat in the process, and that heat energy spreads out, and that increases the entropy of the universe. So energy always finds a way to spread out in some way if a process is spontaneous. If something occurs without outside intervention, then there is in some way. If it does it at high temperature, it tends to be the matter spreading out. If it does it at low temperature, it tends to be an exothermic process that will have the energy spread out and increase the entropy of the universe in that way. If energy can spread out during a reaction, it will be spontaneous. Might be slow, but it will be spontaneous. At high temperatures, and I've mentioned this, energy confined in matter spreads out by spreading out the matter itself. This is like boiling. So if you have water molecules in the liquid phase and you add enough heat, they boil and they move into the gas phase at temperatures above 100 degrees Celsius, and now the matter has spread out. It has more kinetic energy and higher entropy. At lower temperatures, energy is released as heat when new bonds form, something like the freezing of a liquid, which is exothermic. The particles of a liquid will freeze into position, but in the process they form bonds which release energy. And bond formation always releases energy, and the process will be exothermic as heat leaves the system. Energy spreads out in some way. Anytime you have a spontaneous process, energy spreads out in some way. And the reason is because the second law of thermodynamics has to be obeyed in order for a process to be spontaneous. Entropy, the gauge of the machine. Entropy is a measure of how widely energy is dispersed, often defined as a measure of disorder. This is a capital S. Remember that. A system with relatively few equivalent ways to arrange its components has a low entropy, like a crystal solid at very low temperature. This has very few ways that it can organize itself. A system that has many ways to arrange its components, it has high entropy. An example is a gas at high temperature. That's because the gases are crazy town. They move around. They have lots of kinetic energy. They can expand to fill the volume of whatever container they are in. Example of a spontaneous process, expansion of a gas. Here's a gas at 1 atmosphere over here. You open the stopcock and the gas will wind up being at equal pressures on both sides. It'll occupy the full volume that it's allowed to occupy. And it doesn't do it because you're forcing it to behave in that way. It's just statistically more probable that it will behave in that way. So entropy really is a matter of statistics. The more possible arrangements there are, the more probable that that will occur. Dissolution, exchange of heat from a hot object to a cold object, always go from concentrated to more dispersed or dilute. Just imagine 2 molecules of a gas are trapped in one side of a small compartment, and if we remove the wall, the molecules now have more possible arrangements. In this example, the way that it's structured, 6 possible arrangements instead of just 1. If you start mixing, you get more possible arrangements. If you just mix one of these together, you wind up with 16 possible arrangements, 4 times 4. And if we keep mixing, you get more and more possible arrangements. In this example, 36 possible arrangements. I want to introduce you to probably the most second famous equation in science, and this is the Boltzmann equation. Ludwig Boltzmann is its author. He worked in a field called statistical mechanics. Actually, he created the field called statistical mechanics. He was an atomist, a brilliant scientist, and this describes the entropy of any system based on the average of the number of possible arrangements. He worked with gases. He worked with let's say, a liter of gas and a mole of gas in a liter container. And so you have Avogadro's number, 6.022 times 10 to the 23rd number of particles. There's just an astounding number of possible arrangements for that many particles. So it's really impossible to know the specific energy state of an individual particle. So he worked with averages, and he came up with this very cool equation that almost nobody is aware of unless you're a physicist, possibly a statistician, a chemist, and then you have a feel and you've worked with the Boltzmann equation. K, the Boltzmann constant, is just the gas constant divided by Avogadro's number, and you come up with this impressively small number. And I want you to remember that the units of entropy are in joules per Kelvin. You get that from the gas constant divided by Avogadro's number. And W is just the number of possible arrangements. Let me show you Ludwig Boltzmann, pretty impressive dude, very serious-minded, was said to be an extraordinary lecturer. He filled the halls. People loved to come listen to him. And he was what was called an atomist. He believed in the real existence of atoms, which at his time, in his day, around the turn of the century, only about half the scientific community was committed to atoms being real particles. Some thought it was simply a mathematical convenience. And so he would get a number of disagreements with very, very reputable, famous scientists. And as a result, he suffered from bouts of melancholy. And ultimately, on a family vacation, after one of these lectures in which he was resoundingly criticized by a famous scientist, he hung himself. And so, at any rate, if he had just waited a little longer, a few years, he would have been proved correct and recognized worldwide for the brilliant scientist that he was. Instead, he was dead. Hang on, guys. Heat and entropy. Heat displaces atoms in a crystal. So here's your cold crystal. You've got very limited number of arrangements, very orderly in your crystal. They are vibrating. They never stop unless they're at 0 Kelvin. But if you heat that crystal up, they start moving around. They move faster and faster. And so what you wind up with is a higher entropy. So with very few possible arrangements, this is a low entropy. That is a low degree of disorder. So this is low entropy. As soon as you increase the temperature, so entropy definitely can be affected by temperature. As soon as you increase the temperature, you have a higher entropy for your crystal. So this is definitely an increase. Heating stuff up increases its entropy. If we look at atomic motion and its relationship to entropy, really simple molecules have very few modes of vibration. And so if we're talking about a diatomic molecule, it can do this. If it's in solution, it can spin and tumble, but it's a very limited mode of vibration, very limited spinning and tumbling. And so they will have very low entropy relative to a more complex molecule. So the more bonds that you have, the more a molecule can spin and tumble and stretch like this and wiggle like this and spin in different ways. So more complex molecules have higher levels of entropy. In general, the summary is solids will have less entropy than liquids, which will have much, much less entropy than gases. I like to say that gases are entropy monsters. Entropy monsters. Okay, they're just so much more disordered than liquids or solids that generally when you're looking at a reaction, you're trying to predict whether entropy is increased or not increased. Look at the gases. If there are gases in your reaction, focus on the gases. That's going to tell the tale. Small molecules with relatively few bonds will have less entropy than large molecules. So something like, let's say, hydrogen, which is diatomic. You just have this one mode of vibration here. Something like water, which is still a relatively light molecule, but it can stretch and it can wiggle in a number of different directions. So it'll have a higher entropy than a small molecule. Substances at low temperature, low number of vibrations, they have low kinetic energy. They'll have less entropy than a substance at high temperature. Temperature can definitely play a role in entropy. Small amount of a substance, so if I have 1 mole of a substance and then I have 2 moles of that same substance, or maybe I have a larger volume of that substance, so it's more dilute. Small amount of substance will have less entropy than a large amount of substance. Okay, which of the following substances have higher entropy? So here's 1 mole versus 2 moles. Well, it's more stuff, so it's more possible arrangements. If I have 1 mole of a liquid or 1 mole of a gas, gases are entropy monsters. They have more entropy than liquids. If I have 1 mole of a small molecule like methane with only 4 bonds, or 1 mole of octane, which has many bonds, this will have higher entropy because it has more possible arrangements for all those moving parts. And then 1 mole of hydrogen in 1 liter of volume versus 1 mole of hydrogen in 2 liters of volume. More dilute solutions have higher levels of entropy. If we look at entropy changes and we're trying to predict the change, whether it's negative or positive. So if entropy, the change in entropy rather, and that's what we're looking for here, the change in entropy. So we're going to look at what is the change in entropy here, whether it's positive or negative, what is the change in entropy here, and what is the change in entropy here. All we have to do, if we have gases going to liquid, that's easy. I've got 3 moles of gas, and those 3 moles of gas are going to 2 moles of liquid. Now, the fact that it's going from 3 moles to 2 moles is definitely negative, but the fact that it's going from 3 moles of gas to 2 moles of a liquid, this is definitely going to be a negative change in entropy. Okay, so we have a negative change in entropy here. Let's take a look at this one. We're going from 1 mole of liquid water to 1 mole of gaseous water. That's an increase in disorder, and so our change in entropy in this case is definitely going to be a positive value. Here we look at, we've got barium hydroxide. It's a solid crystal, fairly low entropy substance. We've got 1 mole of gas over here on the reactant side, and we're going to a mole of solid, and we're going to a mole of liquid. Honestly, the only thing I'm looking at here, I'm not worried about the barium hydroxide or the barium carbonate. I'm going from a mole of gas to a mole of solid and liquid. This is obviously going to be a negative change in entropy. So this is a negative change. So really, look at the gases. Look at the change in moles of gas if you have gases on both sides. So which of the following processes will be accompanied by the greatest increase in entropy? So let's take a look. We're going from solid to liquid. That's definitely a positive delta S. So that is an increase in entropy, an increase in the disorder of the system, because we're going from a solid to a liquid. This has higher entropy than this. That's a positive change in entropy. I'm going from a liquid to a gas. That is a huge positive change in entropy. That's a big increase going from a liquid to a gas. Big increase in entropy. If I'm looking at this, everything's a gas, so let's just look at the number of moles. So if all your phases are gas phases, just count the number of moles. I have 2 moles of sulfur dioxide. I have 1 mole of oxygen. That's going to be 3 moles of gas that are being converted into 2 moles of gas. That's 3 to 2 moles of gas. That is a negative change in entropy. Okay, so entropy is decreasing. Okay, here we're going from 1 plus 1, that's 2 moles of gas on the reactant side, 1 mole of gas on the product side, so that's 2 moles of gas to 1 mole of gas. And that is definitely going to be a negative change in entropy. It's a decrease.
At liftoff, the shuttle weighed more than 4.5 million pounds, and now 1 minute and 27 seconds into the flight, the main engines and solid rocket boosters have reduced that weight by about half. The solid rocket boosters alone are burning 11,000 pounds of propellant per second, and the external tank is now 3,000 pounds lighter than when it began. Discovery is now 21 miles away from its launch pad and 22 miles in altitude, traveling 2,700 miles per hour. All 3 main engines are working just as expected. The 3 fuel cells are generating power, and the 3 auxiliary power units are all producing pressure. In short, everything performing well. 2 minutes and 7 seconds into the STS-131 mission.